All right, let's look at our results. And we've got these velocities. We've got a nice formula for the velocity in the x direction for the rabbit, and a nice velocity formula in the y for the rabbit. So let's stick these together, and let's actually solve this. So let's say, same question. Let's suppose I ask, what's the velocity of the rabbit at 15 seconds? So all we've got to do is plug in some numbers right here. Put in 15 seconds here, blah, 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 and we're going to end up with negative 2.1 meters per second. Same thing here. If we have 15 seconds, we plug that in, and we're going to end up with a positive 2.5 meters per second. So the bottom line here for our velocity formula will be, just write it right here, our velocity is going to end up being negative 2.1 meters per second in the I, and here we've got 2.5 meters per second in the J. All right, and that tells us what our velocity is at 15 seconds. Now, can we actually figure out what's the magnitude of this velocity total? All right, we can use the Pythagorean theorem again, square the 2.1, square the 2.5, add them together, take the square root, and we can actually find the magnitude of the velocity itself and the angle. I'll leave that up to you once again to do that, so I'd appreciate it if you actually follow through and then figure out what those values are. All right, now our next thought is, let's take a look at acceleration. All right, now we take a look at acceleration. All right, we know that the acceleration, let's say average is the change in v over the change in t. So if we write that down, we can think about that in terms of the vectors themselves. So we've got here, this is a velocity vector now. We've got the change in velocity we have to worry about in the x divided by the change in time in the I. Well, is it possible that the thing is actually changing its velocity in the y direction? Well, we better put that down. So we've got the change in velocity in the y, change in t in the j. Is it also a three-dimensional world? Sure, certainly it is. So now we've got to worry about the change in the velocity in the z direction, change in t, and then we end up with our k vector. So if we look here, we've broken this thing down. Last year we would have just looked at the velocity change in one dimension. Now we can actually add up all three dimensions itself now. All right, so if we take a look through there, we could actually say something along the lines, we've got, this piece, this piece, this piece. All right, now let's take a look at the instantaneous acceleration. So what we could do is replace this with the derivative of the velocity in the x direction, dt, that's in the I. And here we could actually take a look here. Instead of saying the change in velocity in the y direction, we could say d vy sub y dt. That's in the j. And then here we have d v in the z dt, and that's going to be in our k direction. So now we have a nice little formula for the instantaneous acceleration as well. All right, now if we take a look, let's just try a little simplification. This is going to be the acceleration in the x direction, I, plus the acceleration in the y in the j, and then this will be our acceleration in the z, okay, and it's in the k direction as well. So if we look there, we've got ourselves a nice little formula for that. Now, I want you to go back through how are we actually going to use this information to derive the acceleration of the rabbit. Let's say again at 15 seconds. See if you can work that through.